Hey everyone, great to be here. So I think in the first keynote we have seen the huge opportunity of AI. And honestly, I use AI for a long time already. I use ChatGPT on my phone every single day for private reasons and also for professional reasons. It's great, but there is one thing which is missing. So ChatGPT doesn't tell you, I don't know. So with that, it hallucinates, right? This means in the end, it never tells you it doesn't know. Instead, it intentionally gives you a wrong answer. And this is a big problem when you think about the business decisions you make. And so I go a little bit deeper in my talk than the first keynote about the use cases and opportunities to explain you how you can build AI the right way. And in the end, what that means is you provide access to the right data in the right quality at the right time, which is the fundament of providing the right AI use cases. No matter which of these examples you take a look at across industries, you need good quality at the right time. And if you think about a few of these use cases, like customer personalization, when you are a retailer and have a mobile app. So 10 plus years ago, there was already big data. So we sent all that data into a Hadoop cluster. And then we use something like MapReduce or Spark to run a batch process on that data to create AI. And then a day later, we send an email to our customers and told them, dear customer, you bought this product, maybe you also want to buy that product. That's AI, that's machine learning. The problem is, a day later, the customer already has bought this other product on Amazon. So it's too late. So in an ideal world, you do this recommendation while the customer is in your store, before he has left. Or in a similar way, here on the right side, we talk about fraud detection. Actually, I don't know why we always call it like that. We should call it fraud prevention. Because if we ingest all our data into your favorite data lake and store it there at rest forever, and at some point later, we run AI against that to find out there was fraud, that's great, right? That's what AI can do for you, based on historical data. But if they tell you later, it's too late because the fraud already happened. And it doesn't matter if it's a day later, an hour later, or 10 minutes later, the fraud already happened. So in this case, you need to detect AI fraud while it's happening, while the data is still in motion before the payment is processed. And there's many, many more examples across all the industries, right? This is always true. On the other side, however, unfortunately, we have a lot of problems to unlock the data, to take the right action at the right time. And if you think about that, there is not many use cases where later is better than now. Sometimes it's good enough, like for a report for the next day. But in most cases, if you ask the business, it's better to act on data while it's in motion and happening. Unfortunately, there's now two different kinds of estates. There is the operational estate. This is where you do your transaction. And there is the analytical estate. This is where you do your analytics, like creating a report, creating an alert, training analytic model, and so on. And so you see these have very different SLAs and characteristics for uptime, for latency, for compliance, and so on. And actually, the real world is a little bit more complex. So if you don't start a new project from scratch, and in the university you often do, but in the real world, even in a small company, you start brownfield. You always already have existing databases, existing analytical engines, and so on. And so this is really complex to build AI the right way, to provide the right context at the right time, to make your prediction. And this is what I want to talk about today in more detail and give you several customer examples across industries where you see how data streaming can help with this data mess. Everybody has this data mess, and you need to solve it in our more and more data-driven world to enable AI in a better way, without these hallucinations and without being too late. So, in the end, what we want to act from a business perspective, we want to take action on events, right? And an event can be anything. This can be a payment, this can be a chatbot information, this can be an order in a retailer. So there's all these different events. But if your data is already in bad quality, or if it is too late, it's impossible to create AI on that the right way. You could train the best AI model in your data lake. But then, if you don't have real-time inventory as a retailer, what recommendations should your data model do? It doesn't know what you want to sell because you don't have consistent updated information. So you need to have good data quality at the right time, very often now, and then apply your analytic model for inference and predictions. And this is exactly where data streaming comes into play. So the foundation of data streaming is an open source tool, Apache Kafka, that's used by over 150,000 organizations today already. It's open source, you can use it for free, you can build your own products, or you can choose a vendor behind it, like Confluent or anyone else. So the point about the streaming platform in the end is you take all these events from different systems, you combine them, you correlate them, and then either you build a business application or decision within the streaming platform, or you share this event with another application or data lake or database to take action on that. That's the main idea of data streaming. So the fundamental difference to your favorite database, data warehouse, or data lake is that you can take action and process data while it's in motion. In any kind of other persistence engine, you first store it at rest, and then you wait. And then someone else uses a Python script, a SQL query, a REST API to query the data again and take action. But in most cases, that is either too late or it is worse data quality because the data changed already somewhere else. And this is exactly where data streaming fits in here by continuously processing the data after it's created on the fly. So, such a data streaming platform therefore connects to all these different systems. And then you use the data and feed it into other systems. So it's an open data model. So the idea behind that is this black box in the middle. And I know what all of you are thinking. I have seen this before. And this is true because every single integration platform and data analytics platform has a similar marketing slide, right? So it's really important to understand what's the fundamental difference between an event-driven architecture in data streaming compared to your favorite analytics engine like a data lake, data warehouse, or now we call it a lake house, which combines both. So I want to explain this principle a little bit more, and then I will spend 15 minutes or so on several different real-world customer stories so that you see the value out of that. So the main point is in the end, you start from a business problem that's very important. Because you want to make something better, a business process, increase revenue, reduce the risk, reduce the cost, and so on. So a buzzword that comes up these days a lot is the term data product. So what does that mean? That means in the end, you care about a business object. And then with this business object, you can build applications around that. And these business objects, of course, are different across each industry. These data products then are used to build applications. And now, the fundamental difference between having an event-driven architecture and data streaming and the traditional approach is that you only build the data product once. Because after the event is created from your favorite system, like an SAP system, a CRM, a legacy mainframe, and that doesn't need to be real-time. Whenever the event is pushed out of the system, you can continuously process it and curate it and create a data product in good quality. The fundamental difference here is that this data product is created in real time, on the fly. And so on the right side in the architecture where there's multiple consumers, you can consume it in real time, for example, for fraud prevention, to detect a fraud before it happens. So this is an operational transaction. And in parallel, you feed it into your favorite batch platform for analytics, where you train your analytic model for future processes. So you build these use cases on the right side all in the same data product, but they are all consistent data in the same quality, no matter if they're real-time or batch or APIs, and no matter if they're operational or analytical estate. And the big business benefit out of that is the much faster time to market, because you only create the data product once. If you only feed all the data in your favorite data lake at rest, you process it there again and again and again. And then if you need another transaction, you need to process it again, because a transaction cannot be built on batch historical data. And this is really the sweet spot of the streaming platform, where you can create this flywheel. You get the data from the left side where it's produced, you curate it, create good quality in real time at scale, and you can use that for operational and analytical workloads. Is data streaming solving all these problems then? No. It's the data sharing capability. You can't build real-time transactions with the streaming platform, or you feed it into any other engine for real-time analytics or transactions. And this is really what the data streaming platform differentiates from your favorite data lake database, data warehouse, and lakehouse. Again, it's continuously processing the data in motion. This does not mean that everything is or has to be real-time. That's not the real world. The real world is real-time, near-real-time, batch, and request-response APIs, and that's totally fine. But only if the core fundament is event-based, real-time, and scalable. Then you can provide access to all this data from all these different consumers. And that's exactly what data streaming makes different compared to all these other frameworks on the market. So I'm telling the story for years, right? Data streaming is a new software category. I'm also part of our team at Confluent where we brief the research analysts like the Gartner, Forrester, IDG, and so on. And several years ago, well, they wanted to put data streaming into the category of application integration or data integration. So your favorite ETL tool. We always said, no, it's different because you don't just build another tight coupling with integrations. Instead, you truly decouple systems from each other like I just explained. They just communicate via an event. They don't know each other. And they can use their favorite technology, platform, or cloud service. They can be real-time, batch, or request response. It doesn't matter. But at its core, you share the data as an event at scale. And at its core, it's real-time so that you can choose if you need real-time or not. And so here's an example from a Forrester way for streaming data platforms. And so it's no surprise Confluent is a leader here, right? Confluent was created by the inventors of Apache Kafka. So we started from a leading position 10 years ago, and we grew that up to $1 billion in revenue today around the world and across industries. But what's much more interesting to me here is that now even the analysts recognize data streaming is a software category. In the meantime, every large software vendor has a Kafka offering for data streaming. Amazon, Microsoft, Google, IBM, Oracle, you name it. So it's not just Confluent. Because data streaming is so fundamental for building all these use cases. And AI needs to be based on good data quality where data streaming should be the core. Especially if you don't do just analytics, but also transactional and operational workloads. You cannot do a transaction in a data lake. That doesn't make sense regarding the latency and criticality requirements. And this is where the streaming data is different. So here's one more architecture picture, and then I will go into several case studies. So this picture shows in the end what I said before. On the left side, you see all these data sources. And this can be anything. This can be business applications. This can be databases. This can be IoT devices. So in the end, the origin can be high volume, it can be small transactional volume, it can be real-time push notifications from a mobile app, it can be a batch ingest from a mainframe file-based system, it can be anything. But as soon as you feed it into the streaming platform, it's an event. It's a technical or a business information, and as soon as you have it in the streaming platform, you can take action on that. You can process and curate it, more from an ETL perspective, so that you just curate the data to make it good quality and then feed it into the next system. Or you can even build business applications, like, for example, for fraud prevention or for predictive maintenance within the streaming platform. So that's in the end the core, the middle of the picture. And then, as I said before, so data streaming is not solving every problem, but it's the foundation of processing and sharing the data at the right time, in the right context, to the right consumers. And on the right side, therefore, you see many different consumers. If you have low latency requirements or transactional behavior, you typically directly use the Kafka interface to build a new application with Java, with C++, or maybe with a framework on top of that, like Apache Flink. But then there is also still the analytical estate, of course. And for doing things like reporting or training analytic models, this is where your favorite AI platform is best for. That's what it was built for, like the Databricks, Snowflake, the cloud services from the cloud service providers. and so on. And therefore, you can feed it directly as a stream, not just into transactional systems like MongoDB, but also into analytical engines like Databricks or Snowflake. And another common trend we see here in the market, and this is the bottom right, is where the problem in the past was that customers store data again and again and again, and this is very costly and much time-consuming. So there's a new standard emerging in the market called Apache Iceberg. What does that mean? That means in the end, after you process the data in real time and feed it into transactions, for all the analytical use cases, you only store it once in an open table format. And with that open table format then, any of your analytical engines that supports Iceberg can consume it. So you can do your compute, your analytics with your favorite engine, while you only store it once in a data store, typically in an object store in the cloud. And this is a win-win-win situation for all the different vendors and for all the different end users. And so you have the freedom of choice. This is very important. So data streaming is a very different model than your favorite analytics engine. The analytics engines collect all the data, want to keep it, and build all the use cases in there. With the streaming platform, you connect to anything, you can process it, but then you also share the data with any other analytical or transactional technology you want to use. But again, it's good quality, it's curated once in motion, so that you can either use it in motion or store it in your favorite engines at rest to process it there. And with that, I want to talk about a few customer stories so that you get a little bit a bigger picture about why data streaming is used and how it complements other technologies. We are working with customers across industries, so it really doesn't matter what you take a look at. So I have brought a few of my favorite examples, not because of the organization behind it, but because of how you see the value of the streaming platform. I will talk about the first example a little bit more and then rush through a few others. The first example is Deutsche Bahn, so this is the German railway. This is where I live. And if you take a look at this picture, so you see this blue screen there. So when you're in Germany at the train station, you wait for a train. And here it says now, the train to Interlaken arrives at 11:06. So you're there at 10:50 maybe, and it's raining and cold, right? And then you get a notification on the blue display. It says to you, the train is delayed by 10 minutes, 11:16. Delayed by 20 minutes, 30 minutes, 40 minutes. The train is canceled, please wait and take the 12:06 train. So this is a very bad customer experience, but this is the daily life in Germany because we have a very complex train network. We cannot fix that. But at least Deutsche Bahn said we need to fix the customer experience because actually the train was already canceled 6 hours ago in Berlin. But with all this data mass and these hundreds of applications in the middle, we are not able to update this screen here, only in a batch every 10 minutes about outdated information. So we need to fix this. So the first thing what Deutsche Bahn started with was 5 years ago when they said, it's very easy, we just need to have a real-time message broker here to send real-time information. So they started with an open source framework, RabbitMQ. It's a great message broker for real-time. But then they realized, hold on, this operational timetable on the left side, this is not real-time. So just real-time messaging is not good enough. So we need to persist the data somewhere in a storage system and wait until we get the data from the operational timetable. So they installed a storage system. Then they also need to connect the train position information, another application and interface. They realized, oh, sorry, this is an Oracle database. This doesn't fit to messaging in real time. So they added another integration framework, Apache Camel open source, to connect to the Oracle database and feed it into this data mass again. And then they realized, over time, they connect with different technologies to all these interfaces. They have all the data there now, but now still no value because that's not what we can send to this blue display. We need to correlate the data together, so they need some kind of rules engine or processing framework. They realized this is a lot of effort, and they reevaluated. And they realized Apache Kafka, the event streaming platform, provides all of this out of the box in a single solution. Real-time messaging, persistence, data integration, and stream processing. And with that, they reevaluated the project and started again and could deploy this in Germany, which is live today, so that you get consistent information about train delays. On the new mobile app that Deutsche Bahn built, you get real-time push notification. That was straightforward, built on data streaming, And because the new mobile app can use push notifications. It's built for that. This blue display there can still not be real-time because it's a legacy system, 20, 30 years old. It still only allows 10-minute updates. It's a batch system with a file interface. But instead of sending inconsistent information outdated, now at least 6 hours ago after the train is cancelled in Berlin, you can already send this one relevant information to the blue display. Your train is cancelled, please go to a coffee shop and come back 1 hour later. It's not perfect, but it's a much better customer experience. And you see with this story, it's not about real-time data, it's about data consistency between real-time and non-real-time systems. And that's the real-world problem that every single organization has to solve, and that can only be solved with an event-driven architecture and with data streaming at its core. And after Deutsche Bahn has rolled this out, now they could provide this data product, like a train delay or cancellation, to other internal and external stakeholders. So one of the next projects was a cooperation with Google. So in Germany, Google Maps is the de facto standard for routing, no matter if you use the train, the car, the bike, whatever. So because they had built this data product about a train delay already, they afterwards created a partnership with Google so that they integrate the train delay information into Google Maps. So in Google Maps, you see up-to-date, consistent information about your trains. And with that, you can make the right decision. Do I go to the train station? Do I wait for an hour? Or if all trains to that route are cancelled, maybe I have to take a car or taxi. And on top of that, they even could build business models. So you can't read this here, but a very small button in the mobile app, this blue link, this says, buy train ticket. So they even can increase their revenue now by partnering with Google for better customer experience, but then even doing a direct connection to their order management system internally. And this is now the step-by-step evolution we see with data streaming. The first use case was about the internal use case for the customer experience. But then after that, you can reuse the data product, create this flywheel, and without much engineering, you just share this data with someone else to build new products on top of that. So the next example, in a very similar way, from a bank, Erste Bank, operating in many European countries. So they built this new mobile app, Charge. Real-time, instant payment, notifications, all of that, what you expect today as a Gen Z, for example. On the other side, unfortunately, all of their core banking runs in a mainframe. That's batch, that's legacy, that cannot be touched anymore. So they have legacy mainframe, batch, and they have cloud first for new real-time mobile apps. So similar story. So why did they choose data streaming with Confluent? And I'm always using screenshots from our customers when they present it. And what they presented here is real-time no, real-time no. They choose data streaming for data consistency, so that you can do your payment in real time in the mobile app, even though the mainframe can only handle it in batch. But because the streaming platform is not just a real-time layer, but also a persistence layer and integration layer, you can ensure end-to-end data guarantees, even for transactional behavior. This is not something you want to do and try in your data lake. And with that then, similar example. So there is this green box over there. This is the instant payment from the mobile app. In real time, it's transferred into the back end in the streaming platform. So this is not even a streaming API. This is HTTP. That's totally fine, right? Use the technologies you understand. But at its core, it's an event. And then one consumer does a real-time subscription. That's the real-time fraud detection. The second one is API integration, because another interface only does request response. And the third one is an analytical query by a data scientist with a Python Jupyter notebook, where you travel back in time and replay a lot of data in one batch. So you can choose how to consume the data. But it's only possible because at its core, it's real-time, scalable, and reliable. The last example, before I finally also come a little bit to an AI example, is the BMW group, where it's more about IoT sensors. So long story short, BMW didn't know what's going on the shop floor in the factories. So they directly connected their equipment to Confluent Cloud. They streamed all the IoT data in real time into the streaming platform to create a dashboard. First use case, know what's going on. Build a data product in the streaming platform, know what's going on, and building a dashboard. However, then the data was there. So they built a second use case by a different team in the shop floor level, where they connected all these high-volume streaming data from the sensors, they curated it, they filtered and aggregated that, and then they combined it with data from SAP for MES and ERP systems to do transactions like ordering from your supplier. You can build more and more use cases. And after they've presented this at their internal events, a few weeks later, the marketing and sales team came to the shop floor team. They had no idea why. So the marketing team realized there is real-time data coming from the shop floor. The shop floor team thought, what do you need for that for? And the marketing team has completely new business ideas that the other team doesn't even understand. And in this case, the marketing realized, if we can show our customers on the mobile app, if you buy a new car, where it is in the production line right now, we can build a lot of great marketing stories around that. Right? And so this is, you see, you don't always know where your data is going and what it's built for. And this is the same now with AI. So 2 or 3 years ago, nobody talked about GenAI, right? But now you need to bring it into your enterprise architecture. If you're lucky and are using already an event-driven architecture, it's just yet another technology to connect to. And by the way, we talk a lot about generative AI here today in the conference, which is great. It's innovation and new things. Predictive AI is what most enterprises use for many years already. So fraud prevention, predictive maintenance, recommendation in retail, that's predictive AI, which is still awesome, right? And you can create huge value out of that. With generative AI, you can build new use cases. It's a little bit younger journey, and we need to learn a little bit more here. So the opportunities are huge, but no matter if you do predictive AI or generative AI, one thing is clear. You can only do this with good data quality and providing the right context to the right AI application. Otherwise, it will fail. So let's take a look at 2 real-world examples. The first one is predictive AI. Capital One about payments and banking. So they're running their business around event-driven architectures. As I explained before, you connect any system, including mainframes and mobile apps, to process the data. And the one use case with AI is, no surprise, about fraud prevention. So instead of doing just a payment processor and a little bit of risk analytics with some business logic, they embed AI into the real-time streaming application. Because the end-to-end latency between the payment and between the back-end to approve the payment is something like 500 milliseconds. And it has a few more requirements. It needs to run 24/7 with 0 data loss, with 0 downtime, and at any scale for millions of customers. This is what you get with a data streaming platform and with no other technology. And again, to emphasize that, so this is not just about one event. So what you do is typically you take a look at different events. This is called a stateful application. Because you take events from one or more systems, like in this case, it's not just about the payment from your mobile app. It's the payment from your mobile app combined with your historical data in another backend system, combined with the fraud model you apply for model inference, and so on. And this is how you take different events together to take action and make the right decision, which is hopefully we approve the payment because it's valid. And for generative AI, this is my last example. So this is now really where GenAI comes into play. And this is such a hard problem in the real world. So this is actually a story from COVID. So long before ChatGPT, where Expedia was hit by the COVID. Almost all flights were canceled, had to be rebooked or refunded. The hotline couldn't survive that, right? Because it's so many more calls for the same people. So they trained a domain-specific language model to help with answering always very similar questions. How do I rebook? How do I cancel? How do I get my refund? And so on. But the big problem here, and this is now the important part, is not training the domain-specific model. The problem is bringing that model into your enterprise process because it's transactional behavior. You do a refund and repayments. You do a rebooking and call a remote airline system for doing a transaction about a rebooking and a seat reservation. If your AI does not have the latest up-to-date information, this use case will fail. And even if it's 1 minute late, it's too late because someone else has already taken that seat in that plane. And this is how AI can only work very well if you provide the right data at the right context. And so to conclude, is data streaming solving every problem? No. It's part of the architecture, like you see here in this example, where we combine it with your favorite AI technologies, with your favorite batch analytics platforms, and so on. This is really how data streaming fits into that as the central nervous system for data, for operational and transactional systems. And therefore, my last slide, because the time is already up, so good timing, but just to keep in mind, this is a journey, right? And this journey starts with one use case where you add some value with data streaming. It's not replacing an existing system, it's solving a problem. And then you can expand more and more, connecting to more systems, building more and more use cases, and maybe over time then also shutting down some legacy and replacing it with the next generation cloud service. So with this, I hope this was a good overview, also a little bit more about the practical world of how to realize AI with good data quality. We also have a booth outside, so please come there to learn more about data streaming. Thanks a lot.